Our next speaker in the second session is Vieri Mastro Pietro. He's going to tell us about non-perturbative renormalization group for DIRAC fermions, interactions, and quasi-periodic disorder. Vieri, you can share the screen.
Yes.
When you're ready.
Yes. Okay. Is it okay?
Yeah, it's perfect. It's perfect.
Very good. Okay, so hi to everybody. So thanks for the invitation to this very nice talk, very nice meeting. So I will speak about this this non-perturbation group with application on DIRAC fermions. So let me say that the physical properties of emergent DIRAC fermions came out from an interplay of this quantum field theory description, which is essentially a scaling limit, and sort of a continuum limit, and non-relativistic effects, which are due to lattice or breaking on Lorentz invariance and so on. And I would say that really the physical properties are due to this interplay. One cannot really forget one of the two descriptions. So in particular, what I want to discuss is some problems in which you need to take into account large orders. So you cannot rely on a lowest order approximation, but really you need to take into account large orders or any orders, and also irrelevant terms. So the need of irrelevant terms is quite clear, for instance, in the issue of universality of transport coefficients. For instance, transport coefficients are typically finite, but then the relevant terms produce finite contributions. So really, one needs to show that this possible finite contribution really cancel out. So I will use, so I will describe some topic. I will try to make some review or some results. So let me say that such results are analytical. We are using this constructive renormalization group. It's non-perturbative in the sense that not in the sense that we can reach strong coupling, but it's non-perturbative in the sense that we rely on series which are convergent in a mathematical sense. So we use the anticommutativity of fermions to prove convergence of series. Then so we can really get bounds on higher order. So we are sure that we are taking into account non-perturbative effects when this method works. So in particular, I will discuss about some application of this. So in particular, quasi-periodic disorder and universal and interaction, the topic of universality in graphene and in all insulator, and then the topic of bulk edge correspondence. You will see in which sense one needs to take into account large order. So let me start from the first topic. I will start by Weil semi-methods, so they are not really on Flatland, but let me say you can apply this also to two dimensions, but for some reason I will start from this case. So it's a problem of debate, the effect of weak disorder in such systems. They are DIRAC fermions in 3 dimensions. So there are some quantum field theory approach which find stability, while others find the opposite. So this debate is most in the case of random disorder. I will speak about instead of quasi-periodic disorder. It's also interesting because, for instance, for cold atoms, it also can be used as benchmark for other problems. So what is quasi-periodic disorder? So it's a typical case in which you cannot go to the continuum. I mean, it's quasi-periodic with respect to the lattice. So really, you need to take into account the effect of the lattice. So this is what we want to study. So the model I will consider is this sort of basic model for Weil semi-metals, is a lattice model on the square, in which you have this color index 1 and 2. So maybe this is, I mean, in coordinate space, this is typically not very transparent, but in coordinates in momentum space is much clearer. So simply the free energy is given by this matrix, and you see that there is a single point which is vanishing, K1 and K2. So there are 2 points, sorry, K1 and K2 equal to 0 and plus or minus this value of PF. And around these points, you see you have linear dispersion relation, so a sort of relativistic dispersion relation plus order K squared, where K here is the momentum measured from these Weil points. So, so now we want to include many-body interaction, which is, and this quasi-periodic disorder or quasi-periodic potential. So this phi is typically a function like this. You have a sort of sum over n. This is written in Fourier space. And then you have omega 1, omega 2, and omega 3. And now you see, if omega 1, omega 2, omega 3 would be rational, then this would be a periodic function. So one expects gaps. The quasi-periodic case means that you want to consider omega irrational. And also another important assumption in this kind of problems is we assume that the harmonics are exponentially decaying. So now the question, so we want to compute, for instance, the two-point function and see which is the effect of this kind of quasi-periodic disorder, and if the problem is still stable in the presence of this term or not. So let me, so this is a typical problem which you cannot rely on lowest orders. You cannot you cannot get any insight on this kind of problems if you consider only lowest order, because the situation of irrational omega, the situation of quasi-periodic, manifests itself in the behavior of very large orders. So to understand what I mean by that, let me remind a one-dimensional case. So the prototypical of this quasi-periodic disorder is in one dimension is the well-known Aubry-André or Olmos-Mathieu equation. So this is sort of a one-dimensional case in which you have no interaction and you have this quasi-periodic term. So this is a problem which is very much studied in mathematics. And it's typically you have a problem which is called a small divisor problem. What are small divisors? Small divisors are typically the problems which appears in celestial mechanics. You have divisors in which you have the difference of energies, and as omega is irrational, you can have then that is En minus Em can be arbitrarily small. So this produces factorials in the expansions, and then these factorials, but you don't have any divergence, but these factorials can really modify completely the behavior of the system, so you cannot rely on approximation. You really need to understand the convergence or not of the series. Order by order analysis is typically not sufficient. So, for instance, this is again by classical mechanics. You know that in Km to I, for instance, you have these factorials, these small divisors, or in what are called the Birkhoff series for prime integrals. But in one case, the factorial cancel out, and then at the end, this Km to I exists. While in the others, the series are not converging, and the fact that they are not converging means that you have chaotic behavior. So something similar to this happens in this case, for instance, in Wildsen metals and so on, when you have this quasi-periodic disorder. So we want to see what happens in d greater than 1 in the presence of interaction. So in this Wildsen metal or in a quadratic lattice, for instance. So this is, again, we use here renormalization group. The point is that we need to use an exact rigorous renormalization group because we want to take into account all the possible terms in order to decide if the disorder is or not stable, this quasi-periodic disorder is or not stable. So the propagator, as we've seen, is the inverse of this, which H, small h, was this matrix I've shown just before. Okay, this is just this matrix. And okay. So now the idea is that we perform a decomposition of the propagator and we integrate scale by scale. So we are integrated scale by scale closer and closer to the two singularities, to this plus or minus PF. So we write the propagator as sum of propagator of different scale, and as usual in the renormalization group, we integrate and we get a sequence of effective potentials. Now it generates monomials in the fields of all orders. So the crucial point is that now we don't perform any approximation. So we don't know. So all the point is that we don't know which are the relevant terms. So we don't want to make any truncation in this series. We just keep everything. So let me just say that an important point of this method that I want to tell this right now is that by using method coming from constructed quantum field theory, you can prove that you can write this kernels, this W, as function of running coupling constant, and as function of the running coupling constant, they are analytic function. So analyticity is just a peculiarity of this fermionic series. It comes out from a formula that I want just to indicate here, give this just as information, but just to know which are the kind of analytical techniques we use. Essentially, the cumulants or the truncated expectation are written using this formula. So leaving as more, keeping as more as the determinantal structure as possible. And the idea is just to bound these determinants by constant to the end. So we don't produce any factorials in the expansion. So this is just a remark, then you can find an updated derivation of this formula, which is sort of the key technical formula for this approach to organization group. For instance, these physics reports on a more recent work on high energy physics. So just if people is interested in the kind of technique we want to use, but for this talk, maybe it's just sufficient to say that using this kind of formats, we can prove analyticity in the random coupling constants. But of course, the problem is to decide which are not the relevant or irrelevant terms. So let me come back to the problem. So the scaling dimension is this 4 minus 3 over 2n. So the only relevant terms are the quadratic one. But of course, you have infinitely many quadratic terms, right? Because of course, now you have this non-conservation of momentum, and then you have the unclapped terms. So if Q is the momentum measured from the Fermi points, then you have these conservation rules. Then you have this 2 omega n, which is the exchange with the quasi-periodic potential. This 2 L pi, which is the exchange with the lattice, and then also you have the Fermi momentum. So this is exactly, if omega is irrational, this would not cause problems because, as everyone knows, the dangerous terms are the one connecting the Fermi points. So if omega is rational, then all the Fermi points are exactly connected, or they are not connected by a huge quantity. So at the end, you can, the only important terms would be the ones in which you connect exactly the 2 Fermi points, okay? So the peculiarity of this disordered system, of this quasi-periodic system, is that this omega is irrational. So you can have very large processes with strong n, in which you have this quantity which is very, very small, right? So it can be, indeed, it can be small as you want. So it's unclear if these processes are or not irrelevant or relevant. Okay, it would be rational, of course, they would be irrelevant, all the terms in which you don't connect the Fermi points. But in this case, you can go arbitrarily close to the Fermi points, but by the exchange of a huge quantities of this quantity. Okay, so that's essentially the problem. So all the problem relies on that. So are these terms which you don't have exact conservation of momentum in the processes connecting the Fermi points relevant or irrelevant? If they are relevant, then the quasi-periodic disorder would be unstable. If they are irrelevant, the quasi-periodic would be stable. I mean, you don't get any new phenomenon. Okay, so that's the problem. And so I say this here, I'm simply repeating this. So the unclapped terms cannot connect with arbitrary precision the Fermi points. Okay, so they could be relevant. And this is the way, in this language, is essentially the same phenomenon as the small divisor problems that I was mentioning before. I mean, if you look in perturbation theory, these terms are bounded by n factorial. So it's essentially the same. So now you need to use some property of pure number. So in a sense, you need to impose the same kind of number theoretical properties that people impose in classical mechanics to study Kn. So you know that the rational numbers, I mean, has a lot of interesting property. In particular, a very interesting property of irrational number is so it's interesting. You see that to decide if this kind of processes are relevant or not, you really need to use some number theoretical conditions. So in particular, there is a property which is called Diophantine condition. Then for instance, the rationals which verify this condition are as full measure. That says you that this is essentially the Diophantine condition. This T is the norm of the torus. So it says that you can have that omega n can be close to 0 as you want, but up to 2 pi, but you need a very large n. Okay, so this is what is called Diophantine condition, and is is the typical condition one imposes in Km. So using this condition, you can really improve very much your analysis of higher orders and understand if these terms are relevant or not. Okay, it's important also to note that the Diophantine number is full measure, so that's a crucial point. So let me say just an idea of why this condition is useful to conclude that at the end these apparently dangerous terms are irrelevant. So of course, if Q you have these two bilinear terms, and this gamma to the h is negative and gamma is just a constant. So it's a scale of the momentum measured from the Fermi points. So if these two are small, then by conservation of momentum, the difference of these two is of order gamma h. But then this difference is n omega 1. And then you see simply that if you use these Diophantine properties, essentially at the end, if you look to this inequality, you see that you can have processes with two lines very close to the Fermi points, in which the two fermions are close to the Fermi points, but then you need a very huge quantity of transferred momentum, and a very huge quantity is related to the scale of this cube by this inequality. So by using that, and then so this says that if the denominators are small, then the momentum transferred is large. And so you have also this exponential decay of the harmonics, which is very important now. And then using the exponential decay, then you gain some factor here. And then you can prove that indeed all such terms are irrelevant. So this apparent breaking of convergence is not there. So really the disorder is irrelevant. Let me say that in the proof it's essential that you have this that you have this exponential decay of harmonics. And in fact, I believe that is quite, so this one, right? So the fact that these harmonics are exponentially decaying. And in fact, I believe that for other kinds of disorder, if you have a slow decay, it's quite well possible that instead you don't have this stability. So, okay, so this is the conclusion. So the conclusion is this kind of result, this theorem, that it says that if you impose this Diophantine condition, then the two-point function is essentially the same behavior as the non-interacting one. So essentially up to finite renormalizations of the quantities. But as I said, it's important this exponential decay. So indeed, this quasi-periodic disorder is stable. Okay, so there are no phase transition. So in this debate about random case, it was conjectured that the breaking of stability in the random case for Weyl semi-metals was due to ray region effects. Indeed, these ray regions are absent here. So I mean, this is a sort of so confirms this idea that if there is some instability, it's due to ray regions which are present only in the random case. I want also to say that this stability was conjectured in a paper by Hughes, Pixley, and some other people by numerical simulation, and this confirms this result, analytically this result to all orders. Of course, in this theorem, there is this word small lambda that, of course, small, these are analytical estimates. So in practice, probably the strength is quite small, but it's possible probably to improve by some computer-assisted proof that the radius of convergence of this series. But it's important that at least we can prove it's finite. Okay, as I said, the slow decay in momentum space could be relevant if you have slow decay instead of exponential decay. And there are other applications of this kind of systems, for instance, in the Hofstadter model, or in the article of Briandre, or in the XXZ chain with quasi-periodic disorder. I mean, this kind of ideas has been used in this other case. So this was the first application I was mentioning of this constructorization group. You can decide, for instance, if the disorder is stable or not, but you need to look to all orders, right? So because eventually the instability would appear not by a lowest order effect, but by the divergence of the series. Okay, so only proving the convergence of the series you can really say that the system is stable or not. As I said, there are cases, similar series in which is only the convergence or divergence of the series, which says if you have a chaotic system or a stable system. So let me now consider another example of I want to make of these techniques. So this other example instead is more about Flatland, because it's about just graphene. This is a sort of old result, but is a prototype of a number of results we got for transport coefficients. So the question is if is the optical conductivity of graphene perfectly universal or not? But by perfect universal, I mean that it is exactly zero. I mean, it's a sum of zero. If you consider the correction, if you put a many-body interaction, then you have a series of terms. And then, of course, all these series of terms gives finite contribution. But the point is that if all these terms are not smaller, are or not exactly zero. Okay, this was maybe the first result in the sense of the series one. So again, we consider a model we have seen the previous two talks of this today. So you consider the fermions on the honeycomb lattice plus a number of interaction. So again, we don't make any continuous approximation. We just keep the lattice, and then so this delta is these three vectors, and then also I also add this gamma, but this gamma will be discussed later. Okay, so it was proved again by this series that the interaction is really relevant. So you can write a series of terms, and then you see the two-point function is exactly the same form as the non-interacting case up to finite renormalization. It's important to note that these finite renormalization are not vanishing. For instance, the velocity is changed. We compute, and then we got this du plus order u square, and then we have a bound on this order u square, and then in the same way z is modified. So we can prove that there are no phase transition for small u. So that was a mathematical proof. I mean, we can really prove that the series are convergent up to a certain u0. Of course, this u0 is very far from the u0. It was discussed before, in which you have this universality class of gross event. So this we have not computed, but it's surely much smaller than, I don't know, 10 to minus 3. I don't know. It's surely very small, but maybe one can improve. At least, anyway, it is a proof that there are no phase transition. So analyticity is proved. And then as there is no Lorentz invariance, you see the velocity is modified. And the cones remain isotropic by symmetries, but there are are modified. So now one can define the currents. The currents are the sum of the three bonds currents, and then the currents are defined on the lattice using the continuity equation. Then you write the conductivity via Kubo formula. This is the conductivity written in the real space, and then we can do the Wick rotation in this case and prove that in the limit it is equal to the imaginary time Kubo formula. Of course, we have to make the zero temperature and infinity volume limit. This is true only in this limit, otherwise we cannot make this Wick rotation. So if there is no interaction, it is well known, it was a classical result that the interaction is, the conductivity is pi square over 2h. So the question now is that if you switch on this many-body interaction, then you have a series of terms. And the question is, there are not corrections. So of course, these terms are irrelevant, but if you compute them, you get finite result unless they cancel out, right? So you have a series of terms. Also, it's important to note that there were computations using the continuum approximation. If you use the continuum, then you need to put a regularization. This regularization really breaks unsymmetry, so you get ambiguous result. So it is not clear using this continuum model if you get or not universality. And so what we proved, I mean, this is an old result, but it's a sort of prototype of results one can prove by this method, that again, for small u, the conductivity is exactly universal, even if all the other quantities are modified. For instance, the Fermi velocity is increased. Okay. So the conductivity is protected. So it is important to mention, so this was proved here, it's important to mention that this is true only for very weak Hubbard interaction or short range interaction. We got some perturbative result in the case of long range, but still it's much more difficult to get non-perturbative result in the long range case. So which is the idea of this result? I want just to mention, give it with some details, because I mean, you can see the advantage of having these convergent expansions. So the point is that you want to relate the universality to the the regularity properties of the function that you are considering. So at the end, you will see that this universality is related to good regularity properties of the current correlation, and you will see that there are no really need to make computation. I mean, you just get, it is enough to have bounds to prove this universality result. Again, this is not, I mean, this is a sort of series. So I don't mean here up to small terms. So here the game is that here, after the point, there are a series of terms which are ordered by order 0, and then the series is convergent. I mean, it's not simply small. There are no approximations here. So, so the point is that if you have on the lattice, now you have word identities. So these are exact word identities on the lattice. So this connect the vertex function with the 2-point function, and then you have similar word identities for the for instance for the current correlation. So that is the first ingredient. So that's something you have for free. I mean, this theory is well defined. You have on the lattice, so you have exact word identities. So then, so now let's go to the bounds, to the regularity process. So the word identities are, I mean, you get it without computation. Instead, I mean, this, if you use the series we have seen before, I mean, this you use this renormalization group approach, and then you use the bounds on the determinants we have seen. Then you see that the current has this behavior: go to 0 as 1 over x to the 4. So this means that the Fourier transform is surely continuous, but can be non-differentiable, right? Because we have to integrate over d3x. So you're sure that it's continuous, but not necessarily differentiable. Okay, so that is important because from continuity you can rewrite the Schwinger term in the 2-point function so that this equation is true. So the Drude weight is vanishing, but and the conductivity is essentially this limit. So also it's interesting to note that k is even. So if the derivative would be continuous, then it would be even, then it would be 0, because it would be odd in 0. Okay, so if the derivative were continuous, the continuity would vanish. But we know that doesn't vanish by an explicit computation of lower order, and indeed, I mean, indeed, in fact, we see from this bound that the derivative is not continuous. So let me. So this is a. You see there is a strict relation between the fact that something is 0 or not, and the properties of the possibility of making derivatives or not. For instance, in one dimension, this current is non-continuous, and indeed the Drude weight is non-zero. Okay, so we arrive here then. But then, by the renormalization group analysis, and the fact that the interaction is indeed irrelevant according to naive scaling dimension, you can decompose the current correlation in 2 terms. One term which is equal to the non-interacting term plus a correction, RP, and this RP is a very complicated series, but is differentiable. So that is important. We can rewrite all these current terms as sum of 2 terms. One which this is not simply lowest order, right? Because these Z are series in the coupling, so, and then in principle they are non-universal at all. But you can put all the non-differentiable part in this first term. The second term is a very complicated form. It is indeed continuous and with continuous derivatives. Okay. Well, the point is that in the bound you have this extra theta here. So F is a function of u, Z is a function of u, and then you have this extra theta here. And then now the point is that, so how you get from this result the universality? Well, you have done, because now this Z, you have word identities which fixes you the Z. I mean, you have the word identity here that we have seen before, this one. And from that, this is an exact identity, right? It's not an emerging word identity, it's a true one. So, so it says that this zeta 0 is equal to zeta, and then zeta 1 and zeta 2 is equal to the Fermi velocity, which is also a function times zeta. So the expression simplify a lot. This first term is equal to the non-interacting case with a different velocity. And this term is continuous and differentiable, right? So when we insert this expression, also we note that everything is even. Now we make this derivative now, and then you see the first term, which contains all the corrections, is differentiable, is even, so gives 0. The second term is not differentiable, but is exactly equal to the conductivity of a free fermions with a different velocity. But the velocity cancel out even in the free case. So this term is exactly universal. Okay, so that's the point. So you get exactly this result. So there are no correction at all. Okay. So this is quite, so there are nothing there. So you get exactly nothing dependent on the F. So you see this universality is recovered, I mean, by, the first sight, it seems that you lose it because you have all these irrelevant terms which produce shift everything everywhere, but then using regularity properties, then there are cancellation in these apparently irrelevant terms. Okay, so indeed, there was some debate at a certain point, and there was written some computation in the continuum with momentum regularization. If you use, for instance, momentum regularization, there is no way to recover this result because momentum regularization lose deferred by relevant terms, which gives you a finite contribution. Okay, so really, at least this approach is really essential to keep all the symmetries of the lattice and so on. To make this the composition and get this result. So this was the sort of the first result of this kind. In this case, it's interesting because there are no topological arguments to say that the conductivity of graphene is, as far as I know, no one has found a topological argument for saying that the conductivity, the optical conductivity of graphene is universal. It's just done by word identities. So another application of this kind of idea is in the Haldane model or in the Hall effect. So you know, in the Hall effect, you have this universal Hall conductivity. Again, this is the free Haldane model, for instance, just to fix ideas. It is obtained by the graphene model, adding these two terms. Then now you have gaps, and then you have this phenomenon of the integer quantum Hall effect. The universality of this integer quantum Hall effect can be found can be also derived, was derived by topological arguments. But then if you put many-body interaction, it's unclear if these topological arguments are true. And anyway, we want to see if we can use these word identities and renormalization group to conclude universality in this case. In particular, here an interesting question is if there are, you see, there are these transition lines where the mass vanish, and one wants to see even close if that could be. It was even found at strong coupling that maybe new phases appears close to these transition lines. So one want to see if there are new phases in this case or not. So and then also in this case, what we could prove is that the critical curves are different now. So in the case of the model, the lines where the mass vanish are given by this. If you put a many-body interaction like this, like an Hubbard interaction, these lines are modified, but universality is true inside the region. So here is a plot of a second order. For instance, you see there are U equal to 0 are these lines of the well-known regions in the Haldane model. You see with the positive interaction, you have a topological region which is enlarged, but there are no other phases. We can exclude the possibility, at least for small coupling again. And again, the mechanism in this approach for which universality is recovered is again cancellation. You have all these zeta 1, zeta 2, and so on that are functions of the coupling. So apparently, they seem to destroy universality, but at the end, when you put all together, all this effort, all this non-universal term cancel out, and indeed you get even with this unusual form of the interactive propagator, you recover the universality result. I want to mention that there was a big debate in the mathematical physics literature about this universality when a many-body interaction is added. There has been recent proof based on just on topological arguments, but they don't work close to the transition lines. Instead, one advantage of this renormalization group approach is that it works uniformly, even close to these transition lines. So and then as a last application of this idea.
Vieri, can I just interrupt? You've had 35 minutes now, so you have 5 + 5 left.
What means 5 + 5 means 10?
You can have 5 to talk. You can have 10 minutes if you like, or you can have 5 talk and 5 questions.
Ah, okay, very good. Very
Choice
good.
is yours.
I choose 7 talk. So okay, I'm almost finished anyway. So let me say that in this case of examples, in this example, the interaction was irrelevant indeed. So let me just finish with an example, but I will be quick because I want just 6 minutes, in which the interaction is marginal. So the typical example is that this Kane-Mayle-Hubbard model, in which you consider the spin-hole conductivity, and then so the question in this case. It is well known that if you consider cylindric boundary condition, then you have these edge states, and then you have, if you compute the conductance as the same value as the other conductivity, a phenomenon called bulk edge correspondence. And then our question was that if this bulk edge correspondence remain valid also in the presence of interaction. So just to say, in this case, the interaction is marginal, so maybe not so much time to discuss, but then here are just the definition of this conductance. In this case, we consider essentially a spin current, we introduce a shift in the chemical potential, and then, okay, anyway, these are just the definition of the conductance. Maybe what is interesting is that, so we do, then we can compute also the weight and so on. So we do what everyone expects to do, just simply that we are simply keeping into account everything. So we decompose the propagator in an edge part and the bulk part. We integrate the bulk. Then the bulk reduced to the theory, which is essentially one-dimensional, but is not simply a sort of Helical Lattinger liquid. It's not solvable. You have terms of monomials on any orders. You have correction to the linear bands and so on. So the model is not solvable. It's not a Lattinger liquid. It cannot be solved by bosonization. And the point is that even if you cannot solve it by bosonization, we want to prove that even if you have these quadratic terms, the result is still universal, and you have this bulk edge correspondence. So just to say, so maybe I can finish because I will not have so much time, but so the result is that, yes, is the bulk. You see, you have this, the spin conductivity is universal, is 1/π, and instead all the other quantities, the Drude weight and the susceptibility, instead verify the Lattinger liquid relation. So maybe it could be, it's a bit surprising in a sense that here you have exactly 1, in the other case you have this K, which depends on the interaction. But this is, so this one wants, but is in a sense it's surprising. Let me just say that the idea is simply this, that we compare with the theory, one-dimensional theory, which can be solved, not by bosonization, but by word identities. So just to finish, the crucial idea is that we write the current of the b-dimensional system as the density correlation of the one-dimensional system by times constant, which are multiplicative, and constants which are additive, functions which are additive. This is what, so maybe this I skip this, but this is what exactly we get by the renormalization group analysis. So at the end, we get all these functions, this correlation, which are sort of one-dimensional plus this Z, and this Z are complicated function of the interaction. But then we can fix the value of the Z by the word identities of the lattice theory. And if you do that, the miracle happens, and then this you get here 1. So this all non-universal effect cancel exactly only in the all conductivity, in the spin-hole conductivity, and not in the other term. Okay, so maybe this was more or less the message I want to give. maybe as a last comment, one can try really to consider also results which are not uniform in the velocity. So one can ask what happens if you don't neglect the quadratic terms. And I want to really consider case in which the quadratic part is greater than the linear one. And then, for instance, in one dimension, you need to do a sort of two regime randomization group analysis. Okay, and then you can see that really the results can be done uniform in the velocity, and you can even recover a lot of features of the Excel solution by beta ansatz, for instance. So really, this non-perturbative randomization group reproduces a lot of properties even found by beta ansatz in the special case. Okay, so that's more or less what I wanted to say. Maybe we can skip this. So the message is in relevant terms and non-perturbative effects can be important for a number of issues like the one I presented. Of course, main problems in this approach is to go to strong coupling, that's sure, long range, which is really complicated, and also, of course, the relevant terms at t greater than 0. So you see, we have seen that the relevant terms does not change the behavior essentially in t equal to 0 in this case, but for t greater than 0, you cannot make this big rotation that I was saying. So that's really a problem. So maybe if I think now should be in time, right? So I hope. So that's it. So.
Perfect. Thank you, Vieri. Thank you. Are there any questions? You can either speak out loud or you can put something in the chat.
Yeah, I had a question.
Yes,
please.
Yeah, so it's about this whether there's a renormalization of the connectivity. So remember, there's this work by Maslov and Stone in 1D where they showed that I think you got a different result for the conductance, whether let's say you had a larger liquid, and then if the leads were Fermi liquid or not, then you would get a factor of K in the conductance or not. So I was wondering whether in your approach, in this axiomatic approach or constructive approach, whether you could reproduce, whether that results could show up in this way of doing the calculation.
I think there the idea, if I remember well, yes, I know that, but I think that in that case the idea was different, right? Was a sort of different definition in taking into account the boundaries. I mean, what I'm presented here is not a similar idea. We have simply integrated out the bulk terms, and then, as I said, we got this finite normalization which are fixed by the word identities. So if I remember well, in that paper instead was a sort of taking into account of the boundaries terms. I think it was a different mechanism in that paper.
Yeah, that's right. It was a reservoirs, I guess. Yeah,
yes, was a reservoir. Here there is not. Yes. In fact, now in fact, I remember they were saying that was necessary to take into account the reservoir. Instead, I mean, what I'm playing here is that is exactly what you get. What I said. I mean, I gave this definition of conductance I've written before, and then simply do the computation, but without neglecting anything, and then you get this 1/pi. So I think it's okay. All the Z disappears. I mean, but simply they are fixed by the word identity. So, but of course, if you miss some irrelevant terms, then you will this term will this cancellation will disappear.
Okay, thank you.
Are there any other questions?
Yeah. May I ask?
Yes.
No.
Yes.
Yes. I don't understand you. The unclap terms describes the ion or phonon processes.
I mean, you have these quasi-periodic terms, which can be seen as sort of disorder. And then, of course, these quasi-periodic terms you have two kinds of this. The unclap is just the effect of the lattice, right? Because the momentum is conserved up to 2π. But then also, or 2π over a if the step is 1/8.
Yeah.
And then you have also this external quasi-periodic potential, which exchange other momenta.
Yeah, thank you. And second, my questions, do you have any information about effective electron mass dependence on the band gap?
I think it's possible to compute. Yes. Yes. I'm not. Of course, the band gap. If you're speaking about the first part, right, the quasi-periodic, you must understand that the gaps are very complicated in this case, right? Because if you have a rational omega, then you have a finite number of gaps. Now, if you have this irrational omega, then the number of gaps becomes infinite. So you have a sort of fractal structure of gaps. So I guess that the dependence on that would be very, very complicated because you have this fractal, right? So if you have a rational omega, then P over Q, then you have Q gaps, right? But if it becomes irrational, then the number of gaps become infinite. So it's a sort of, you get a Cantor set of gaps.
You haven't analytical relation, yeah? This
Yeah.
dependence.
Yes, not yet.
Not yet.
No.
Thank you.
Okay, thank you, everyone. Can we thank Thierry again for a really interesting talk? Yes, we do.
Thank you.
I've not really worked out how to do applause on Zoom.
Okay.
There are various solutions. Okay, thanks, Thierry. Our next speaker, we're very happy to have Ian Affleck, who's going to tell us about Hubbard-Majorana, the Majorana-Hubbard model.
Okay, thanks for the invitation. Nice to be at the conference. Sorry, it's online instead of in person. So, it says my internet connection is unstable. Can you see the screen? Okay.
You can see the screen perfectly, yeah.
Good, okay. So this is a collaboration. I've had quite a few papers with our Armin Ramani, who was a postdoc at UBC. He's now a professor at Western Washington University. Marcel Franz is a colleague of mine at UBC. Dima Pekulin was a postdoc at UBC. He's now working at Microsoft Station Q. Tarun Tumaru is still a graduate student. Kyle Weimer was my PhD student. He's now working for a financial company in Vancouver. And Zhao Yuzhu was a visitor from China who went back to China. So the outline of the talk, motivation and model, talk about the one-dimensional case, then I'll talk about the two-dimensional case, square lattice and triangular lattice, and then finally some conclusions. So the motivation and the model. So the macroscopic number of Majorana modes are predicted to occur if a layer of ordinary superconductor is placed on a strong topological insulator in a transverse magnetic field. So we have a Majorana fermion predicted to be at the core of every vortex, as shown here. Majorana fermions are candidates for qubits. This has led to great interest in them. So it's been the main focus of research at Microsoft Station Q, also by Charlie Marcus at the Niels Bohr Institute and various other places. So various experimentalists have claimed to see Majorana fermions, but this has remained controversial, especially in cases where they see the Majorana fermions at the ends of quantum wires. There have also been some experiments that have claimed to see the Majoranas at the vortex cores. So interaction effects involving Majorana fermions have not yet been studied experimentally, but at least two experimental groups are interested in studying them to test our theoretical predictions. So a Majorana mode is predicted to occur at the center of each superconducting vortex. Majorana modes can tunnel between vortices and interact with each other with short-range interactions proportional to exponential minus r over xc, where xc is the coherence length for the superconductor. And very importantly, the tunneling amplitude can go to 0 if the gate chemical potential of the topological superconductor is tuned to a special value. So that basically means that we can tune the ratio of the coupling constant strength to the hopping strength to infinity. So therefore, it's of interest to study the effects of interactions, even when they're very, very strong.
Ian, can you hear me?
Yes.
We're not seeing the slides advancing. We're still looking at slide 4.
Oh, I moved to slide 5. Okay. That's strange. You can't see slide 5?
I can't.
Something's gone wrong here.
Yeah.
Okay, let me try to reshare here.
Can see slide 5 now.
Oh, good. Okay, good. Thanks. Okay. So we've studied the shortest possible range interactions in these Majorana models, and we're calling this the Majorana Hubbard model. And I'll show you exactly what those interactions are. So we have a Hoppling amplitude T, and we have an interaction strength G. And we consider G over T of either sign because it's not so clear, because we're dealing with superconductor, it's not so clear if the interactions could be effectively attractive or repulsive. So we've considered both cases. So I'm going to first of all talk about the one-dimensional case. Then I'll talk about the two-dimensional square lattice. And then I'll talk about some results on square lattice ladders. And then I'll talk about the triangular lattice ladders. So first of all, the one-dimensional case. So here's the Hamiltonian. Can you see page 6 now?
Not yet. Not yet.
Oh dear.
I don't know if you're in slideshow mode yet. Because I can still see along the left-hand side of the screen, I can see all your thumbnails.
Okay, let's see, what's the problem here? Okay, I could switch to a PDF instead of a PowerPoint, if that might help. You can't see page 6?
We can see page 6 now. I mean,
Okay.
the PowerPoint's perfectly visible. I just wondered if you'd be better in slideshow mode.
I think you should switch your video off, Ian, because there's low bandwidth on your end.
Okay, switch off my video.
Yep. There's a warning came up that said on my end that your bandwidth is low, so it might help.
Yeah, I'm actually on a cabin on Hornby Island, so maybe it's not very good internet, so maybe it's part of the problem. Okay, so you're suggesting I don't think I want to switch off the audio. So anyway, you can see page 6 now?
Yeah.
Okay, so here's the Hamiltonian. So the gammas are Majorana fermions, so gamma J dagger is gamma J. These are the anti-commutation relations. So and we consider the shortest possible range hopping, so nearest neighbor hopping, and we have interactions that are on 4 sites. We can't have any on-site interactions because gamma J squared is just 1. So the interactions have to involve 4 sites. So there's no conserved particle number in this model, but they're important discrete symmetries. And this model can be studied by field theory and also by density matrix normalization group, and we've used both techniques. Okay, can you see page 7?
Not yet.
Okay, try it again. You see it now?
No. Oh, there it is.
Oh dear.
No, it's come
There
up
it is.
now.
Okay, comes back. Okay, good. Okay, so Majorana is in some sense like to pair up and form complex Dirac fermions. So we can combine a pair of Majoranas to form a Dirac fermion. So for example, we could combine the Majoranas in a site, even site and the odd site to the right to define a CJ. And if we do this, then we can confirm easily that I gamma 2J plus 1 is twice C dagger J, CJ minus 1. And half the interactions become very simple. They're simply can be written as kind of a standard nearest neighbor interaction in terms of Majorana fermions. The other half of the interactions are very complicated, and I'll write them down momentarily. So notice that there's kind of a sign change here. So if G is positive, we effectively get attractive interactions. And if G is negative, we get repulsive interactions. This is because of the I squared factor coming in. There's no conserved charge. So the mean field density is determined by interactions. So at a mean field level, there are 2 mean field ground states for positive G, which correspond to attractive interactions. We can either pair up Majorana fermions on 2J and 2J plus 1, or 2J minus 1 and 2J. And if T is positive, then at the mean field level, these Majorana states will be empty. So we predict 2 ground states from a mean field theory in the attractive interaction case. Okay, I'm going on to page 8. Can you see page 8?
Let's give it a moment.
Okay. Can you see it now?
No.
Oh dear. Go back to page 7, page 8.
Yeah, here it is.
There it is. Good. Okay, great. So this is the full Hamiltonian written in terms of complex fermions. And I've defined Pj to be twice C dagger J, Cj minus 1. So one of the hopping terms is simply T times Pj. And one of the interaction terms is simply Pj times Pj plus 1. Then we have a very complicated hopping term that involves a pairing term and a hopping term. And then we also have another interaction term that involves actually 3 sites. So if we only keep the first T term and the first G term, this is the mean field theory. And remarkably, this turns out to be qualitatively correct at large G, as we've confirmed using DMRG techniques. Okay, so on to page 9. Page 8, page 9. Let me know when you can see page 9.
Yeah.
Good. Okay, so if we have repulsive interactions, so G is negative, then there are actually 4 ground states, because now this changes the sign of the fermion-fermion interactions. So it's a little bit like the spinless fermion model, which is what one gets from mapping from the XXZ spin chain. So now we actually get 4 ground states because we get a alternating field empty, and there are 4 ground states. And this corresponds to a charge density wave. And we verified that these phases also occur at strong coupling using DMRG methods. Okay, page 10. Let me know when you can see page 10. Page 9, page 10.
Not there yet. Yeah, there it is.
Okay, good. All right. So the non-interacting case we can solve quite easily. So we can just Fourier transform. So we define a gamma k. And notice that gamma minus k is gamma k dagger because gamma j's are Hermitian. And if we take gamma k to gamma minus k, then we change the sign of the exponential. So this means actually we can restrict the rho1 zone to run from 0 to pi, or pi over A, where A is a lattice site. And I've set the lattice site A equals to 1. So we can easily diagonalize, and the Hamiltonian becomes this. So this is a curve of what this looks like. And notice that the ground state just has all states empty. And they're only particle excitations, not whole excitations. And this is a property of Majorana fermions. And low energy excitations are relativistic. So we can produce excitations near 0 or near pi. Okay, so on to page 11. So page 10, page 11. Let me know when you can see page 11. Page 10, page 11. It says my internet connection is unstable. Maybe that's part of the problem.
Yeah, it's there now.
Can you see page 11?
Yeah.
Good, okay. So we can go to a relativistic continuum model by defining basically right movers and left movers. So the right movers have momentum near 0, left movers have momentum near pi. And now we can write the relativistic field theory. And it's just a relativistic model for non-interacting Majorana fermions with right and left movers. And the velocity turns out to be 4 times t. So these operators, these gammas have dimension 1/2. So this non-interacting Hamiltonian has dimension 1. And if we write the lowest dimension continuum interactions, they take the form gamma right, dx gamma right, gamma left, dx gamma left. We have to have the derivatives here because gamma right squared is simply a constant. And this has dimension 4 because each gamma has dimension 1/2 and the derivatives have dimension 1. So this is highly irrelevant at weak coupling. So we expect to get a free Majorana dispersion, at least for small enough G. Okay, on to page 12. Page 11, page 12. Let me know when you can see page 12.
Yeah.
Good. Okay, so at sufficiently large G, we find the broken symmetry phases as predicted by the mean field theory. Remarkably, the transition at positive G occurs at very, very large G at 256, but for negative G, it occurs at -3. And Paul Fendley actually found a slightly modified model where the phase transition occurs at a much smaller value of G. And he did this by actually just having the interactions on 5 lattice sites instead of 4 lattice sites. But I'll just discuss the case where we have the nearest neighbor interactions. So the fact that this G is so large makes the numerics very challenging. And Armin Romani was the main one who did that numerics. So the correlation length is infinite for G between 0 and 256 because we just have this non-interacting model. And it only comes down to perhaps a few hundred lattice sites at G of infinity. So the nature of the second order phase transition for G of 256 is interesting. So the critical line with G less than 256 corresponds to the one-dimensional quantumizing model. So minus sigma zj plus 1 plus h sigma xj with h tuned to 1. So the translation symmetry keeps the model critical if we ignore the interactions. And the symmetry is actually translation by one site, which takes gamma r to minus gamma r. And this forbids the mass term gamma r gamma L. Okay, on to page 13. So let me know when you get to page 13.
Yeah.
Okay, so the Ising model symmetry is called Kramers-Wanier duality. And this is a symmetry which actually takes h minus 1 to minus h minus 1 for h near 1. So it takes us from the broken to unbroken symmetry phase. And the Ising transition becomes first order when we insert a large enough density of randomly located vortices. And this transition can be realized by using spin 1s instead of spin 1/2s and inserting an SZ squared term which favors SZ equals 0. Okay, so on to page 14. Let me know when you can see page 14.
Yeah.
Good. Okay. So this is the spin 1 model. So we have the SZJ squared term, and we have a region here. So as we vary delta, if delta is small enough, we're in the we have a first order transition as we vary gamma. But if delta gets large enough, we actually have a we have a second order transition. I mean, if gamma is small enough, but we have a first order transition if gamma. If delta is large enough. And this is sort of obvious if delta is 1, because then we just have a transition from the SZ equals plus or minus 1 states to the SZ equals 0 states. So for G slightly bigger than 256, we predict fermions and bosons. So the model is predicted to be supersymmetric, and we can map this tricritical point in the Ising model, called the tricritical point, is been studied by conformal field theory, and this point is known to be supersymmetric. So we predict that we have a supersymmetric phase transition occurring in this Majorana fermion model. Okay, on to page 15. So page 15 is it's two-dimensional square lattice case. Okay, on to page 16. Can you see page 16?
Yeah.
Good. Okay, so here's the Hamiltonian for the square lattice. So now we have nearest neighbor interactions, but now we have a alternating sign for the horizontal interactions and not for the vertical interactions. And this is because we require that we have 1 flux quantum per plaquette. This actually leads to this sign change. And we have interactions, again, we can just take to be on plaquettes. So we have interactions on these square lattices. And we could also add a second neighbor hopping term, which is shown here. So the signs of the hopping terms are determined by, as I mentioned, 1 flux quantum per plaquette. And interactions, again, are basically G less than 0 is attractive interaction, and G less than 0 is repulsive interaction. Okay, and on to page 17. Can you see 17? Okay, so page 17 only has 1 sentence.
There it is.
Says, good. The T2 term breaks time translation time reversal and parity symmetry and changes the phase diagram significantly. So we're especially interested in the case where we only have nearest neighbor hopping, which leads to a more interesting phase diagram. Okay, on to page 18. So let me know when you can see page 18. Yep. Okay. So phases are characterized by spontaneously broken symmetries. So what are the symmetries of the Hamiltonian which might get broken? So we have translation by one site in the X or Y direction. We have pi/2 rotation symmetry. And if T2 is 0, we also have time reversal and parity symmetry or spatial reflection. And it turns out that PT, product of parity and time reversal, is a symmetry even if T2 is non-zero. In addition, there are a number of emergent symmetries that occur in the low energy effective field theory. Okay, so on to page 19. You know, you can, good. Okay, so these pairing phases also break rotational symmetry and parity symmetry for T2 equals 0. And depending on the sign of G, we can either obtain a ferromagnetic or antiferromagnetic pairing phases. So this is so if we calculate I gamma m n, I gamma m n plus 1, we get a plus b minus 1 to the n. So we get an alternation. And this is shown in there. There's two ground states where the fermions pair up vertically. There's also two ground states where they pair up horizontally. So altogether, we have 4 ground states at a mean field level. And again, pairs of Majorana forming Dirac fermions. And again, for positive T, all energy levels are empty at the mean field level. We'll go down to page 20. Let me know when you can see 20.
Yeah.
Okay, so for 20 now we have alternating basically filled empty, filled empty. And now we actually have 8 ground states because we can translate, we can form out pairs this way or this way. We can translate by one side. We can also rotate and form pairs horizontally. Okay, on to page 21.
Yeah.
So these pairing phases also break rotational symmetry and parity symmetry for T2 equals 0. What about time reversal? So time reversal takes gamma mn to -1 to the m plus m gamma mn, and also I to minus I. So this symmetry is broken by second neighbor hopping because these two gammas stay the same, but there's an I here which changes sign. Okay, so now let me talk about a field theory normalization group approach and nature of critical points. And I'm on page 22 here.
Yeah.
Yep, good. So non-interacting case, we can calculate the dispersion relation. And this is what it looks like for nearest neighbor and second nearest neighbor. And we can restrict ourselves to a Brillouin zone, which kx runs from 0 to pi. Again, because gamma k is gamma minus k dagger. And also because we have alternating hopping, we can restrict the Brillouin zone to pi in the y direction. So for T2 much less than T, we have low energy excitations near 2 points, 0, 0, and pi 0. And we have approximate Lorentz invariance. So this is the dispersion relation if we Taylor expand at small energies near k equals 0 or pi. So it looks a little bit like graphene. We have 2 valleys, but now we have Majorana modes, not ordinary complex fermions like we have in graphene. Okay, on to page 23.
Yeah.
So the low energy field theory has 2 species of 2 component Majorana fermions. And this is because we have 2 low energy points. And we can combine these to make a single Dirac fermion. And this is the low energy Dirac fermion theory. Turns out there are terms that also break the U1 symmetry, and I'll mention those in a minute. But it turns out these are irrelevant. So these are the terms that we get in terms of the Dirac fermions. So this is the relativistic Dirac fermion, non-interacting Dirac fermion Hamiltonian with the usual gamma matrices. And I've set the velocity to 1. And this is the lowest dimension interaction. Okay. So in addition to emergent Lorentz invariance, there's also an emergent U1 symmetry or particle number conservation. So the interactions are irrelevant in the renormalization group sense. because the fermions have dimension 3/2 in 2 + 1 dimensions. So for small enough interactions, we expect will be in the non-interacting phase. We can write this interacting term this way, and we say that we can think of this as being a pairing term. So for positive G, this is an attractive pairing interaction. And for strong enough positive G, we expect to go into a superfluid phase. And this corresponds to a ferromagnetic pairing phase. Okay. There's also a higher dimension UN breaking term. So for T2 = 0, the fermions are massless in the G less than G critical phase. Can you see page 25?
Yeah.
Yep. And the superfluid transition involves a massless Goldstone boson as well as a massless fermion. So this transition, it turns out, is supersymmetric. So this transition has been studied previously in other models, but this is the first time it's been studied in a Majorana model. So for non-zero T2, the fermion's got a mass, fermion's got a mass, and the transition is now not supersymmetric. It's kind of a standard Wilson-Fisher transition. But with the T2 = 0, we get a superfluid transition, and it's the usual UN breaking 2 + 1 dimensional transition. Now, it turns out that there are terms that break the UN conservation. There's this term, so psi1 dx psi1, psi2 dx psi2, minus psi1 dy psi1, psi2 dy psi2 plus Hermitian conjugate. But with Kyle Waymer, we showed that this remains irrelevant at the critical point using the epsilon expansion. So we can probably ignore this UN breaking term. Therefore, we predict this supersymmetric transition to occur in this model. So note that this lattice model evades the Nielsen-Ninomiya theorem. We only get one channel of Lorentz invariant fermions in the low energy model. And the reason is that the UN symmetry is broken in the lattice model. So unlike a model with complex fermions, we only get one Dirac fermion occurring here in this model. Okay, on to page 27. So can you see 27? 26, 27?
Yeah.
Good. So we studied 2-leg and 4-leg ladders numerically and also analytically. So it turns out with square lattice geometry, by combination of analytic and DMRG methods. So in the 2-leg case, there's an exact U1 symmetry, it turns out. So we can see this by defining complex fermions. So we have two legs, so we can define a complex fermion on leg 1 and leg 2, so gamma M0 and gamma M1. And the horizontal hopping term becomes this, so it preserves the U1 symmetry. The vertical hopping term has this form, so these both preserve the U1 symmetry. So if we impose periodic boundary conditions in the vertical direction, the vertical hopping term vanishes. Then by the Jordan-Wigner transformation, the Hamiltonian takes the following form after the Jordan-Wigner transformation to spins. So we have exactly the XXZ or XXZ model. And we see that I gamma M0, gamma M1 becomes -1 of the M sigma Zm. So that the antiferromagnetic order occurs for G bigger than 1/2. This corresponds precisely to the mean field ground state that we predicted. So we see that the mean field predictions are actually correct, and they correspond to what we get in the spin chain. Ferromagnetic order occurs for G less than -1/2, and this corresponds to this mean field ground state. So we see this is also correct. Can you see page 29 now? 28, 29.
Yeah.
Good. Okay. So for the 4-leg case, there's no exact U1 symmetry. The model's not analytically solvable except at infinite coupling. But we analyzed it with DMRG. So to analyze the infinite coupling limit, we define complex fermions again on ladder 1, 2 and ladder numbering the ladder 0, 1, 2, 3. So we form a complex fermion on ladder 0 and ladder 1 and or leg 1 and leg 2 and also leg 2 and leg 3. Then it can be seen that the interaction terms preserve fermion parity in each rung, unlike the horizontal hopping term. So the horizontal hopping term breaks the UN symmetry, but the vertical hopping term actually preserves it. Okay, on to page 30. You see page 30?
Yeah.
Good. So with strong coupling, we can restrict ourselves to only two states with fixed fermion parity on each rung. And we can map these two states into the XY model with the Hamiltonian. So this is the interaction term. So again, it basically is an XY model, except it involves ZZ and XX. Unlike the two light case, this model is gapless with no broken symmetry, except for fermion parity. If we had a small hopping term, this produces a gap. So for small t over g, we can ignore horizontal hopping since it changes the fermion parity in each rung. This can be shown to increase the energy by an amount of order g. Okay, on to page 31.
Yeah.
You see, yeah, good. So the vertical hopping just gives a perturbation t times sigma z m for even fermion parity, or t times sigma xm for odd fermion parity. So either or odd number of fermions on the lattice sites. And both of these models map into the basically the XX or the Ising model. So this leads to gap states with spins ordering in the Z or the X direction for even or odd fermion parity for G positive. So for even fermion parity, the order parameter becomes sigma Zm. And this corresponds to Majorana's pairing up to form DIRAC fermions, as I've discussed. Okay, on to page 32. You see 32? 31, 32. Can't see 32 yet?
No, it normally does the trick when you say two numbers, but it hasn't yet.
Okay, 31, 32. Okay. Can you see 32?
No.
Oh dear. Okay, try it again. 31, 32.
Yeah. Yeah.
Good. Okay, great. Okay, so on the other hand, for odd fermion parity, gamma m2 and gamma m3, gamma m0 go to minus sigma xm. So we get the other mean field state. So in fact, we're getting perfectly the mean field states that we predict by mapping into the spin chain at strong coupling. Okay, on to page 33. Okay, can you see 33?
Yeah.
Good. So for positive G, we only find one transition. This maps into complex fermions. Ignoring interactions, we get one gapped complex fermion, one gapless complex fermion. At small g, we can integrate out the gap mode. Then we find the UN breaking transitions are irrelevant, and the UN preserving interactions are of standard spinless Luttenter-liquid form or umplap form. So we thus predict a Kostelis-Thalwis transition into a gap phase at sufficiently strong G. And this agrees well with the DMRG results. So we're not actually seeing supersymmetry in the four-leg ladder case, but we expect to see it for the infinite number of legs. Okay, now I want to go on to the triangular lattice. That's page 34. Can you see 34, 33, 34?
Yeah.
Okay, so triangular lattice, we have some hopping terms that are again determined by having one flux quantum per plaquette. And now the interactions are more complicated because we take the nearest neighbor interactions, so-called Majorana-Hubbard model, but now we actually have four plaquettes on which we have interactions, which I've drawn here. So if we solve the non-interacting model, there's actually a gap, unlike what happens in the square lattice case. So we have these two different bands with a gap in between them. Okay, can you see 35?
Yeah.
Good. So now we have three types of plaquettes, as I showed you in page 34. So now the mean field state only minimizes the energy in 1/6 of the plaquettes. So mean field theory doesn't predict Majorana pairing to form DIRAC fermions. That's consistent with our DMRG results. So we find that DMRG results in the four-leg ladder do not break symmetries even at strong coupling, consistent with the mean field results. Okay, so I have conclusions, but I can go back and show you a few more pages if we have a little bit more time, which I guess we do. So here are the conclusions. The Majorana-Hubbard model in various lattices has rich phase diagrams. Majoranas like to pair up to form complex fermions for strong enough coupling, breaking discrete symmetries, and supersymmetry can be realized in both 1 and 2 dimensions. So I have a bit more time. So let me go back to the one-dimensional case and discuss the full phase diagram in more detail. So for positive G, well, actually for positive or negative G small enough, we have a range of parameters where we just have the Ising model.
What number do you want to be on now?
Oh, page 37. Can you see 37 yet?
Can't see 37. Oh, yeah, there it is.
Good. Okay, great. So we have this range where interactions are irrelevant, and we just have the Ising model.
Sorry, Ian, it went again. It appeared for an instant. There it is.
Okay, can you see it now?
Yeah, yeah.
Good, great. Okay, so we have this small enough interactions. We have the Ising model. Then we have the tricritical supersymmetric point. And then we have this broken symmetry phase at large enough G over T, which is bigger than 256. And then for negative G, we get this gap fourfold degenerate state predicted by mean field theory for G over T less than -3. Then we have this interesting intermediate phase, which is a combination of Ising plus Luttinger liquid model. So let me explain what that means. So on to page 38. So we can see this by just adding a third neighbor term. Can you see page 38?
Not yet.
Okay,
There it is.
38. Good. Okay. So second neighbor hopping is not allowed by time reversal symmetry, but third neighbor hopping is allowed. And this leads to a dispersion relation, which is 2t sine k plus 2t3 sine 3k. So on to page 39. Okay, 38, 39. Can you see 39?
Yeah.
Okay, so for T3 equals 0, this is the dispersion relation I showed earlier. For the critical point T3 equals T over 3, we actually get a cubic dispersion here instead of linear. And then for T3 larger, we get this dispersion relation. So now we have Majorana modes at 0 and pi. And now we have Dirac fermions at K0 and pi minus K0. So this means we have a combination of Majorana and Dirac fermions. And the Majorana fermion interactions are irrelevant, but the Dirac fermion interactions give the usual marginal interactions. So psi right dagger, psi right, psi left dagger, psi left. And also we get a Majorana Dirac interaction. So the first term is a standard Luttinger liquid interaction. And this continuously changes the Luttinger parameter, which determines the critical exponents. Go on to page 40. Can you see 40? 39, 40?
Yeah.
Good. Okay, so we can write the Majorana Dirac interaction, but this, it turns out, involves some oscillating phase, unless K0 happens to take the value pi over 4. Also, it turns out that we can look at the Luttinger liquid parameter G, and it turns out that initially this is irrelevant because it involves 4 fermions and 2 interactions. So this is irrelevant unless the repulsive interactions are very strong and the Luttinger parameter becomes less than 1/4. And also the wave vector K0 has to be pi over 4. So this transition into the C equals 3/2 phase at G equals minus 0.3 is a Lifshitz transition, and it's involves a cubic dispersion relation, so it's not a Lorentz invariant transition. Can you see page 41?
Yeah.
So the transition out of the C equals 3/2 phase into the strong coupling broken symmetry phase occurs at G equals -3. This occurs because K goes to 1/4 and K0 goes to pi over 4 simultaneously at exactly the same value of G of -3. So we can calculate K and K0 using DMRG, and we get the finite size spectrum. We come to this remarkable conclusion. Okay, so that's everything I wanted to say. Here's the conclusions again, page 36, and I'm finished. So thanks for paying attention.
Thank you, Ian. That was a pretty intense 38 minutes, I have to say.
Okay. Yeah.
Thank you very much.
Okay, you're welcome. Questions?
There must be some questions, yeah.
I do have a question. Is there an intuitive understanding why the critical point is, I mean, the value of the critical point is so much different in the positive G case than in the negative G case?
I think that there was a later paper. I'm going to have to remember. Let me post who wrote that paper. But I think somebody had some kind of explanation. I guess it just has to do, I guess, with how the coupling constant in the relativistic field theory depends on the coupling constant in the lattice model. So for some unintuitive reason, coupling constant varies much more slowly for positive G than for negative G.
Okay.
Actually, negative G rather than positive G. I think that's the explanation. Quite surprising, I agree. And as Fendley and O'Brien pointed out, if you just modify the interactions slightly, so you have interactions on 5 sites, so they have interactions on 1, 2, 4, 5 instead of 1, 2, 3, 4, then the transition occurs at a much more reasonable, much smaller value of G, turns out.
I see. So in a sense, it's a coincidence that it's in a sense fine-tuned that this value is that large. Is that correct?
Yeah, it's quite surprising and no intuitive reason. Yeah.
Thanks.
Okay.
I have a question as well. Ian, can you hear me?
Yeah. Yes.
Okay.
Go ahead. Hi, Joseph.
Yeah. Hi. So in this this massive phase away from the tricriticalizing QCP, so I guess it's a massive deformation. So you're turning on some primary field of the CFD that preserves the supersymmetry but makes it massive.
Exactly. So we're actually studying that right now numerically and analytically. So we think that if we're just into the broken symmetry phase, but close enough to the tricritical point, we should be in a massive supersymmetric phase. Whereas on the other side of G, supersymmetry is spontaneously broken, it turns out. So in the Ising phase, supersymmetry is spontaneously broken, but in the broken symmetry phase, we expect supersymmetry to be present. So we expect to have degenerate fermions and bosons. And we are confirming that numerically.
You know what's the operator that is being turned on? Do you know specifically which primary?
Okay, so there's an operator. The only relevant operator, it turns out, preserves supersymmetry. Okay, I can't remember right now what it is. It was discussed decades ago in the original study of the tricritical. Actually, I think there was a paper by John Carty and an Italian who worked with him. Remember his name?
Musardo? No, not Musardo.
Musardo, I think. Yes, Musardo. Yeah. So they showed that the only relevant operator was supersymmetric.
Okay. So is it a fermion mass or is it like psi bar psi? Or
we turn on a fermion. We expect to get a fermion and boson mass, and we expect to get degenerate fermions and bosons, which is quite surprising because we only have fermions in our model.
Right.
And in fact, we think that the interesting thing to study are solitons and anti-solitons. So if you have an even number of sites, we get soliton anti-soliton pairs. And it turns out that the soliton involves a Majorana fermion because we sort of go from forming Dirac fermions on 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 to 2, 3, 4, 5, 6, 7. And there's one Majorana fermion at the soliton. So a soliton anti-soliton pair has 2 Majorana fermions, and these can interact and form either a fermion or a boson, depending on whether the state is filled or empty. And we think that these have to become degenerate, and that's what we're working on proving that right now. We're expecting to finish up a paper on this fairly soon.
Okay, very interesting.
Good question. Yeah.
In your numerics, are you effectively at 0 temperature when you?
Yes, we only study 0 temperature. That's right. Yeah. So I should say that there were some mysterious phase transitions we saw in the 4-leg ladder, which were not predicted to occur in the mean field theory. And whether these occur for infinite number of ladders, or only occur for 4-leg ladders, is a bit of an open question right now. So I think more numerics are definitely required right now to settle these issues. Likewise, in the triangular lattice, we saw some mysterious transitions we didn't predict in mean field theory for 2-leg ladder. So whether these occur for the infinite 2-dimensional case or only occur for 2-leg ladders is a bit of an open question. Any more questions?
Can I have a question, please?
Yes,
Please,
go ahead.
Pavel, go on.
So you mentioned that you obtain a kind of lattice action which has only one DIRAC fermion, which apparently contradicts the Nielsen ninomia.
Yeah,
right?
exactly. Yeah.
Can we say that in this case the one particle, the single particle Hamiltonian is non-Hermitian because U1 is broken, or maybe
No, it's Hermitian, but it breaks U1 symmetry. We only have one Majorana fermion per lattice site instead of one complex fermion per lattice site, and that's how we managed to evade the Nielsen-ninomia theorem. So the symmetry is, I mean, the model is Hermitian, but it breaks U1 symmetry.
Okay. Okay, thank you.
Yep. Any more questions?
I think we may have run out of questions. So
Okay.
thank you, Ian. And can we
You're
thank
welcome.
both Ian and Vieri for 2 excellent talks in this session.